got 2 days to finish your review, and then on Friday we're going to collect the reviews, and then the grade will be hopefully assigned over the weekend, and then the week after next, the course is officially over. Okay. All right. So let's get down to the business. So we're going to use the last 2 lectures to kind of give you a roadmap of where graphical model is going toward and how flexible it can be for you to work with graphical models. So in the almost entire process of the lecture, we kind of developed the understanding that a graphic model is probabilistic graphic model, and therefore learning graphic models is about maximizing the likelihood of the data underlying a model, right? And then you are going to get parameters. And sometimes we use conditional likelihood as a alternative. So from here, today's lecture, I'm going to show that in fact, graphic model really does not only mean a probabilistic model. It can be just a graphical structure that inspires a optimization problem, as we see actually in the graph-induced sparsity estimator. In here, you actually see a full model, and the estimator of the model can be built on criteria that is different from a likelihood function. Okay, and sometimes you can get a very powerful estimator by combining a number of different objective functions, such as margins, likelihood, which means fitness of the data, and predictive accuracy and stuff like that. So let's begin by talking about this maximum margin learning of graphical models. All right, so just a little bit historical account, or maybe a mini review. So we all know this classical paradigm of learning predictive models, right? The setting is that you get some input data X, which is going to be in a high-dimensional feature space. And then your output is Y, which is a labeling space, like a binary space, or maybe a discrete set of labels. And then your goal is to learn a predictive function H of X, based on which you can inference about the optimal assignment of Y, which is by maximizing this predictive loss function. Okay, and then this function, which is the predictive function, is usually a log linear model, right? And which translates to weighted combinations of features defined on data. And then this G is just a cover function on top of it. And then your goal is to define a loss function. Okay, the loss function sometimes can be this function itself. It can be something else, and then plus this is a shrinkage function or a regularizer. Sometimes we use it to define constraints, such as we want some W to be sparse. And this actually can be understood in a very generic way. Sometimes you can call this a prior in a Bayesian sense. Then this amounts to a prior distribution of the weights. Right? So just to make things more concrete, here are examples that you already know from 701, which actually fall nicely into this picture. Right? So for example, if you choose the loss function to be the conditional probability of the label given the data, and then you basically are working on logistic regression, right? And then you can also introduce a prior distribution on the weights, and then you get a Bayesian estimation of the weights. Okay. So this is logistic regression or Bayesian logistic regression. Basically, what you do here is a maximum likelihood or a maximum a posterior probability estimator. And a seemingly very different paradigm is the SVM. People call it a non-probabilistic framework or a total frequentist framework, where you are solving this problem, where you minimize the L2 norm of the weight vector, and And maybe here you also minimize the predictive margin loss. And then here you have every instance or every training example to induce something called margin constraint, right? So these two looks to be very different, although they all belong to at least this case where you have a general predictive loss function, and this one is in here. What is G? If you want to make the connection, in logistic regression, the G takes a form of what? A sigmoid function, right? It's a sigmoid function. G exponential to the WF divided by 1 plus exponential to the WF, right? What is the form of G in terms of a SEM? It should be simple, right? It should be 1, the indicator function, right? You basically just do okay, come on, you need to know how to use your learned ways to make prediction, right, in SVM. In SVM, it's just a linear predictor. You are going to test your example, based on this, sorry. Right? Or in the simplest case, you actually are doing this. And you will ask whether it is greater or smaller than 1, or maybe greater and smaller than B. That's how you do SVM, right? So I hope you don't get lost in the very basics of how do you use the stuff you actually tried very hard to learn, okay? But the message I want to send here is that, even though they look very different, they actually are all special cases of this very general notion of defining a loss function and do a loss minimizing estimation. In here, the loss function corresponds to a log loss, we already said, and in this case, the loss function is actually a hinge loss. Okay, probably people heard about that already. The hinge loss basically is that suppose that I have the weights and maybe the score. And then the log loss was like this, right? And the log loss was like it is like this, and the hinge loss was like this and that. There is a flat thing in the middle, which actually gives you, you stop penalizing basically the function once you are within a margin. Right, and here you have a continuous drop of the margin, of the loss function. So you can go to the 701 to review all this, but I want to make sure that you understand these two things are actually not much different in terms of the general learning framework, in learning predictive models. And there are, competing advantages, for either framework. In the logistic regression, it is a probabilistic model. Therefore, you have all this benefit from a probabilistic semantics. You can introduce prior distribution. You can introduce hidden variables if you want to build a hierarchical model. And the hidden variables sometimes can be interesting in reducing feature semantics or complexity and stuff like that. And we will see some examples later. And the SVM has some other advantages, right? People like SVM apart from its simplicity due to availability of a software. But statistically or machine learning wise, it has a number of key advantages in the design. One is you have this kernel trick, which allow you to automatically go to a non-parametric predictor. It also has something known as a dual sparsity, which means that your decision boundary depends on a few points on the decision boundary. Therefore, that gives you a nice generation error bound, right? And you have strong empirical properties and all this, the results and so on. All right, so this is what we call the classical predictive model, which is for the so-called unstructured prediction, which is roughly this case. You have all these features, and then your prediction is a binary or a discrete one. And therefore, in these cases, the graphical model kind of device are not very useful because there are not too much structures. Okay, at least in the quantity you are interested about, like these labels, there isn't a structure. But there are many other prediction problems which known as the structure prediction problems, where your labels are more complex, right? For example, here, imagine you do a part of speech tagging. That means for every word in this sentence, you need to give it a tag, right? Therefore, your prediction is a sequence of labels. And they are actually also not independent labels. Okay, the label of the first entity is dependent or related to the one on the second part. In computer vision, same thing. Your goal is to make prediction on every pixel in this picture. Therefore, given this input feature matrix, you are going to output a label matrix, and we already learned about in our early example that if you make this prediction independently on every pixel, you are unlikely to get interesting results. Right. Therefore, you want to define a graphical model, maybe for the labels at least, if not together with label and also the features. Right. So here is this very famous example that a colleague of mine, Ben Tasker, used in one of his famous paper that I'm going to talk about in a second. So this is a problem known as the OCR, object character recognition problem, and so this is the actual data, okay, which is scan of a handwritten word, and your goal is to decode it into the actual word. Okay, so I think most of people here, if not all of you, have no problem recognizing this to be that. Right? But if I just give you a picture like this, okay, and a picture like this, I believe you will have a hard time, in generating two different labels for this, right? You may call this an R, right? You may call this a C, depending on what writing habit you have. And the reason we can come up with this brace, the right spelling, is because we implicitly built a model, within our brain already over the characters, right? Which means that this R, a C probably will happen very infrequently after a B, if you already have a high confidence of this character being B, right? And likewise in here, if you recognize A already, then R after A is probably less likely than C after A, and so on and so forth. So that means you want to hopefully make use of a sequential structure to tie together all the labels. Right? So this defines an instance of the structure prediction problem. Okay. And you have image segmentation using Markov fields, and we used this example earlier already, right? By defining the Markov fields, you can now connect all these different labels with some kind of potential function, which encourages them to be sharing a label, or if not, then there must be strong evidence against that. And yet another example is in NLP. When you do parsing, the example I showed earlier, your part of speech tagging should follow a syntactically valid kind of a tree, to make sure that they are correct. If you just ignore the tree structure, on top of the labels, and just look at the leaf nodes independently, then chances are you are not going to be able to do a correct prediction. All right, so now that brings us to this new paradigm of structured prediction problem, and we want to use a structured prediction graphical models. Okay, and that's where we start to see graphical model, actually is used, in this setting for complex prediction, and we ask the question about whether the training of such model can have more diversity as we had for training classical prediction models, such as the binary prediction models. There we have a lot of flexibility. We can use log loss, we can use hinge loss, which is not a likelihood function. We can use many other things. But if we are talking about the structured predictive graphic model, I think the only thing we learned so far are two approaches, right? So one is, of course, we know what is HMM already. HMM is actually for training structure prediction model as well, right? You are going to build a generative model using this graph, and your goal is to basically learn, call this y, call this x. Your goal is to basically learn the joint probability of x and y, and then write down the conditional probability of y given x. That's basically what the HMM is going to tell you. And your goal, your training basically is based on maximizing the likelihood of data, right, under this model. And then later, during the semester, we learned another probabilistic model called conditional random fields, right? And there, the goal is to maximize the conditional probability of the label given the x. And here, the conditional probability is defined on the structure labels. Okay, it's a whole sequence of y given x. And if you still remember, the form of that function, you probably can recall that the likelihood, this conditional likelihood on structure label given the structure input is actually also a logistic loss. Right? It is an exponential function over some weighted sum of features, which actually takes this form. The only differences of this versus a logistic regression is that this feature vector, okay, is now different from the previous ones. The previous feature vectors is suggest, some functions defined on the input, okay, and it has very little to do with the y, the labels, right? Because y has only one, of the other label. But in this case, the y is playing an important role in designing the feature. You actually have, this kind of features. Like you can define pairwise potentials on every labeling, kind of a pair, and then to make sure that maybe certain combinations of label should be favored over adjacent kind of predictors. Right? So this is basically the conditional random field. And today I'm going to show you now another model, which is known as the maximum margin Markov network, which is actually the counterpart of support vector machine in this structured prediction domain, which means that you actually can also train this structured prediction model as what is trained in CRF using a large margin principle. Okay. And sometimes people call this a structured SVM instead of a Markov network. But the structured SVM is to emphasize the affinity or the similarity to SVM formalism. But I like this name better because it reminds you the deeper connection of this approach to graphical models. And then you actually can go way beyond what we have here and introduce some other complexities. Okay, so that's the plan for today's talk. This is actually a very important paper, okay, in the field of machine learning. I remember when Ben actually proposed this work when he was a student at Stanford. I was still a student at Berkeley, and he came to Berkeley and gave this talk. It was highly debated. And it took us a while to understand what he's doing, and then we also tried to figure out whether that really makes sense at all or not. But it turns out that many people like this framework, and that started a whole effort of studying structured SVM type of framework, and also a lot of theoretical framework in designing better inference algorithms, optimization algorithms for solving that. So now let's take a look at how this algorithm, how this model is about. So I wrote this algorithm in a way that is trying to remind you the simplicity side of the design, right? It is actually also about introducing, a weighted combination of features, okay, but now defined under a hinge loss, okay, and then here are some additional terms that you can add to enhance the loss function. But after all, I want to send out a message that this model and this model belong to the same framework of loss minimization over structured prediction models. And if you look at what you have in here as the classical unstructured predictor and the modern structured predictor, the only differences is actually in the design of these feature functions. Otherwise, statistically, they are very much the same thing. Okay? That actually gives you the kind of the upper side of the whole story. It is fundamentally a very simple kind of design, although the resultant solution can be a little bit more demanding due to the introduction of the structures. But I do want you to actually now build this correct kind of lineage of graphic models. From logistic regression to CRF amounts to taking the single unstructured label to the multiple structured label, and the roadmap from support vector machine to the maximum margin Markov network amounts to take this very simple feature built on binary labels to the complex features built on structured labels. Okay, so that's basically the roadmap. So when we solve this problem, there are a number of challenges, okay, including how to make a sparse kind of bias so that the model become interpretable, how to introduce prior knowledges, how to introduce latent variables, and so on. And we're going to now study whether the framework here offer tools to address this problem, and if not, what additional machinery we want to bring in to actually further empower this framework. Okay, so let's start this taking a look of this structured model from its very basic form. So now our goal is to actually learn this predictive function H, which is built on maximizing the score function. The score function is actually defined as a weighted sum of features. Okay, this is the simplest case. That's what you actually see in SVM as well. There isn't. I could have also included a G function in here, right, to make it some fancier loss. But here, my G function equals to an indicator, or just a 1. And here, the thing that makes the whole problem complicated is actually not this part. It is the solution space, right? Because here, your y is not in the space of a +1 and -1. It is in the space of all possible labels that you can imagine for a label of length k. Then how many possible labels you can come up with? It's exponentially complex, right? All right. And then this feature design is also now having the ability to take advantage of structures, right? So here I can now break this down into a sum of potential-based features, and this P is basically a unit. You can imagine they are corresponding to the potentials or the cliques in the graph to give you unit of substructures that you want to encode information on. Therefore, you can now actually come up with complex features. So for this part, I'm not going to drill into because we have a couple of lectures in the early part of the lecture talking about the feature designs in graphic model and so on and so forth. So you can basically design the graphic model like this. And so this basically corresponds to your early notation of theta t times, okay? And, okay, so C corresponds to the cliques, okay, in the graphical model. Okay, but now I'm not going to use a probabilistic kind of a loss function on that, which I could use if I'm doing graphical model, but now I'm going to remove that part and think about some other ways of learning the theta. In this case, I call them the W to draw connection to the SVMs. All right, so now let's look at our training example. By the way, this is a prediction problem, therefore we talk about the supervised learning, okay, because otherwise the prediction cannot really being optimized against. So the label now are the Y stars, and we want to make the model such that the label, okay, in the training is actually what to maximize this loss function. Okay, that makes sense. And but in another way, we are not only happy by having the model, which is W, such that the right label is the maximizer of this. We also make the prediction risk small. Okay, and that's basically the SVM spirit. we want to make sure that the correct label is greater than any other incorrect label, okay, and by a margin. Okay, so that means that I have, for example, many ways of learning this W function, this decision boundary, okay, but I want to make sure that it is in the right orientation, that my margin is the biggest, okay, on training examples. And I can even augment this margin to make them result dependent. For example, now I have the right result and a alternative result, which are two labeling sequences. And the two labeling sequences can be different in different way. It is, in the binary case, you have +1, -1. Their differences are all the same, right? But in this case, if it is a k-character labeling, you can measure the Hamming distances or the number of matches between two sequences. And therefore, you can actually now define a margin function that is dependent on the amount of differences that the two alternative labeling can make. So that's basically our constraint, right? We want to make sure that this is the maximizer, and then they subject to the margin constraint like this. This is known as the structured margin constraint, okay? Okay, so now look at the differences, right? So in here, in SVM, what we have is the following. We are going to learn the weight, okay, by minimizing the L2 norm of the weight subject to margin constraint. And in here, the margin constraint is basically due to the yi taking either +1 or -1, right? And but other than this, everything I talked about earlier in the maximum margin Markov network remain the same, right? It is also a bunch of features, and you have now a y which is more complex, right? And that additional complexity due to the labeling space is actually indeed quite worrisome, when you want to adopt the SVM framework. In the original SVM framework, how many margin constraints do you have? Want to give a guess? You have a training set of n examples. Now, how many margin constraints you have? Mm-hmm. N, right? Every sample induces a margin constraint. Yeah. Okay, so let me remind you, you guys are senior students in graphic models or in machine learning. Instead of understanding SVM to be a software that you can call, you actually want to know what each loss function is, at least, if not solving it. Okay, you may be okay, you don't know how to solve it in the optimization program, but at least the formulation should be clear to you, right? So in SVM, you need to know this, and then there is this per sample based margin constraint. But when translating to the structured SVM, we are going to have a lot more constraints, right? For example, in this case, we want to make sure that the correct label brace gets the maximum score in here. But what about all the other labels? There are labels like AAAA, this one. They are the alternative labels, which are incorrect. We want to first make sure that the score due to this label is going to be smaller than the right label, right? And also, they should be even maybe separated by a sufficiently big margin. So how many such constraints do you have? Exponentially many, right? So that's a very, very expensive constraint function. For n examples, you need to have exponentially many number of constraints. So we need to really now try to figure out a way to deal with that. So first of all, we need to understand now that the maximum margin Markov network in the brute force sense is no different from SVM. So we have this clean formulation already. Okay. Other than that, in here I have a kind of innocent notion, but quite actually malicious if you look at into the complexity. But at least this is no different from SVM. I could just stop here and ask you to call a software or a black box to solve maximum margin Markov network, and your only requirement is to understand where this feature come from. They come from a graphical model. Right? So that's one level of understanding. But I want to say a few more words about how to actually solve this program in a more efficient fashion, other than just a brute force implementation of a convex optimizer over exponentially constraints. Because here, many of the design exposes, first of all, the ingenuity of Ben in inventing this whole machinery, but also to tell you how this graphical model knowledge can be helpful in making the solution simpler. Okay, so here we have this many number of examples, this number many of constraints. One reduction from including all these constraints is to basically reduce them to the most violated constraint by just one constraint. So basically, suppose that your solution is in here, and you have many other suboptimal solutions. Each one corresponds to the, so this is the right label. This is the wrong one, wrong one, wrong one. And this particular formulation basically says that this one should be above any of this one. Right? We need to test every one of them. But if you already know that one particular solution, W prime, is the worst, or is the best, other than this correct solution, okay, the next best one basically in your solution space, then as long as you imagine, you ensure that this correct solution is greater than the best next solution by a margin, then it must be also better than all the other solutions, right? So therefore, we're going to solve this problem instead. Okay, I'm going to still do a loss optimization in the space that is the labeling space except the correct label in your training example. Okay, and call them Y prime. And then I can now replace this part, okay, with this one, where I only care about one such label, one such margin, okay, due to the next best solution. Okay, and that basically, if you know the solution already, then that reduce the number of constraints into polynomial, right? The number of samples. So that's the best case. We have this, and replacing the margin constraint over all configurations to margin over one next best configurations. Okay. All right. So this looks pretty nice, except now that we need to solve this subproblem, which is again in an exponentially complex space, right? So symbolically look nice, but actually, in solving the problem, you don't really lose a lot of, gain a lot of efficiency. Okay, but on the other hand, the formulation becomes a little bit different than before. It is now taking the form of a minimax formulation, right? You are minimizing this, and here you need to solve a maximization problem. Then the next reduction of this, because we really want to hopefully push this into just a single line of constraints rather than a constraint with a hidden complexity of exponential, right? So how should we do that? So now let's look at, first of all, what amounts to exponential complexity in our general knowledge base. Usually exponential complexity comes with a combinatorial solution, right? You basically have discrete solutions of multiple dimensions, and then you need to exhaust all configurations of all these discrete solutions. And that's no good. Sometimes, from our intuition of solving integer programming and discrete optimization, we found that it is easier sometimes to turn them into a continuous operation problem, right? In a continuous operation problem, even though the space is infinitely many, but it is smooth, it is differentiable, therefore you can actually get down to the optimal solution rather quickly, right? So that's a next step that was proposed for this problem. Let's turn this max problem from a discrete optimization into hopefully a continuous operation problem. Okay, take this form into that form, where Z is in the space of continuous numbers. But hopefully, these two have some kind of equivalency. Maybe we can show that this continuous form is a controlled relaxation of this one. Okay, so that gives you the next number of transformation. So in here, we express this loss function directly using the label sequence y. But so label sequence is a complex one because you have all possible vocabularies that you use to label a target. And when you are taking the y itself to be an argument, you lose certain mathematical manipulability. Right? For example, you cannot take a derivative over y and stuff like that. Right? So our first change is to rewrite the solution, the label, into a form of an indicator function. Right? For example, let's take this sequence as an example. Suppose this y takes the outcome to be AB, ABB. Okay? Then an alternative way of encoding this answer is to use 5 indicator functions. Okay, the first one being 1, 0, 0, 0, 0. This is, by the way, a 26-dimensional indicator, right? And then the second one is now B. Therefore, the second bit is 1, right? So, in a sense, a sequence of a collection of z's is equivalent to the y label without taking care of the interdependencies between adjacent labels. Right? And now, if we also want to have a structure, say I want to basically build a graphical model over z or over the y originally. So this is y1, y2, y3, and instead, if we want to do both, a graphic model defined on singleton potential and also pairwise potential, then we need to also use some higher order features, indicator functions. For example, now I can have this pairwise indicator to indicate whether a particular doublet of configurations is present in my outcome label. Right? So in here, if the first 2 is AB, then Z12 has a 1 in here and a 0 elsewhere. Right? So it looks like this is a pretty kind of luxurious way of generating a outcome like this. This you have only 5 characters, but it is in the huge combinatorial space. But in here, you have a lot of indicator function vectors and matrices, but it is in a space of simpler structure. At least your vocabulary is just 0 and 1. Okay. All right. So with a little bit clean up, now you can rewrite the original loss function, which is this one. Okay. Equivalently into this. I hope you can figure out how to write this. Right. This is basically to tell you each particular edge potential and node potential. That basically tells you how much score you want to give if a particular label is happening. So this, for example, xkn correspond to the case position, take a n configuration, and likewise in here. Right. And just to make things more cleaner, this whole thing can be now expressed as a linear function over the z. Okay, z being, of course, the collection of vector labels and matrix labels. Okay, and then we need to have constraints on the z. Okay, or if we are really doing the original direct transformation from a discrete label, then the z can be only 0 and 1. Then we have total equivalence. We are still in a combinatorial integer programming type of problem, right? But if we want to make a relaxation, we could do the following, right? Making every z indicator to be a positive number. That's the first relaxation, but continuous. And then we can also encode a normalization constraint, meaning that in every position, you can only use one label. Okay, only one of the characters is possible. Therefore, you have this self-normalizing constraint. And then this is what? This is the adjacency constraint, meaning that if you have a pairwise feature, on this particular node, they should have the agreement, right? So if you look at this, this is almost like our belief propagation, constraint, where the singleton and pairwise potentials have to have a local consistency in here, and also self-normalizability, right? So essentially, I'm treating the z to be also almost like a belief message, okay, to be propagated on the graph, and they are now, used as a surrogate to the discrete solutions. Okay, so at the end of the day, this entire problem gets reduced to this, okay, which is now maximizing, again, a linear function, okay, and subject to the constraint that z is satisfying a linear constraint in here. Okay, so here I didn't insist on z to be discrete. Therefore, you can solve this problem by using many of the continuous optimization procedures, such as, block gradient descent, integer program, interior points, many of the black box algorithms. All right, so our original problem, okay, now is this, and the transform problem is now taking this form. We replace y with the z, and the z is constrained but relaxed into continuous value. In fact, if you go deeper into the, into the formulation, there are cases where the optimal solution to z actually is, an integer one. You can actually recover, the exact solution. But in some other cases, more complex cases, you actually do not have an integer solution to z, even though, in the space includes integer solution. Then you need to do some kind of decoding, to turn a fractional z into a discrete z. And then I have a little bit more kind of clean up of the formulation to make the problem even simpler. If you use the theory of Lagrangian duality, you can actually realize that this constraint maximization problem is equivalent to its dual, which is a minimization problem. Okay, and that's because of the strong duality of this problem. This is a convex, okay, in both the loss and also in the solution. And if you have a convex operation problem in the convex domain, then the dual of that is having strong duality of the primal one. Basically, their solution should be the same. Therefore, you have this equivalency. And once you have this, it actually helps you to reduce this problem even further, because you can drop the minimization sign, and put the minimum operator in here only once. And then here, you actually don't have to minimize it again, because the minimization is already happening in here. Okay? So that's basically a few steps for you to now achieve a pretty handy solution to the maximum margin Markov network, which look like here. Okay, it is very similar to the original SVM procedure, except now that your feature functions is inspired by the graphic model potential functions. And here I have, there can be a number of solution packages, based on, solving a quadratic programming, and you can, have a lot of different ways of, coming up with, efficient algorithms for solving that, which I'm not going to cover. Okay, so clear about the whole framework, maximum margin Markov network. Okay, so now I want to actually show you a nice experiment arguing for the advantage of this over the unstructured SVM version. So the problem is the OCR problems we said before, and the naive problem that people would use is of course this, right? You just ignore the dependencies between the labels. It's not like you want to ignore, but it's because you don't have a way to even incorporate it if you want to use SVM. SVM basically takes one picture of a character and make a discrete prediction, right? So that gives you a score of a 27% error basically, which is not bad, right? Raw pixel-based prediction. And this is, by the way, not even a trivial SVM already. It is multi-class SVM because you have 26 outcomes possibly, right? And you can do, of course, one versus other, which is quite trivial. But this multi-class one is even better, by making the prediction through one calculation. And we know that conditional field was invented to encode structure, but based on a probabilistic graphical model. and where the labels are not coupled, so that certain label combinations are favored over others. And but it is not based on a margin loss. Okay, it is based on a maximum likelihood loss. Maximum likelihood means that you need to build a distribution over the data, and then the observed pattern has the best likelihood. Best likelihood does not necessarily always mean you need to have a best prediction, right? And the score is basically better than this, but not by much. Okay. Oh, by the way, so let me review a little bit. Do you know why a best likelihood estimation may not be necessarily a best predictor?
Because your assumed model may be parametric.
I'm using the same model. Remember that the model means that your definition of the feature x, y, and the weight. It's the same model, right? I'm using exactly the same feature to encode a model. I'm just training it by a different criterion. Here I train it by a logistic loss, right? In here you train by some other loss function.
It has to do with the variance of the maximum likelihood estimator?
Maximum likelihood estimator actually gets you a consistent estimator in the end, right? And if you have a lot of data, for example, you actually may reduce the variance pretty nicely. It is not minimizing the prediction error. But why not minimizing that, but maximizing the likelihood isn't a good idea? Okay, so this is where I want you to really depart from merely remembering equations and get the intuition about what's happening in probabilistic modeling, right? So suppose you have this decision boundary, and you have training points in here and here and here, okay, on both classes, and you may also have a few weird points very far away from that. Let's put this on negative, right? And what does SVM do? First of all, SVM is to find basically a decision boundary which makes sure that points on both sides of the decision boundary are maximally separated in the sense of a margin. Therefore, it's trying to make sure that this point has this margin, and that point has this margin, and this margin should be maximized, instead of finding, for example, this decision boundary, which has a small margin, right? What does maximum likelihood estimation do? Do you know? It is basically estimating a density function, okay, of the data. Density function is not defined dependent on only points around the label, around the boundary. If I have a weird point in here, maybe somewhere in here, my density function need to also take care of that. Okay. Therefore, I may actually end up having a very strange density function. Okay, just because I have points in here. Okay, and at the end of the day, it will actually drive my decision boundary to be this tilted one. Okay, because my density estimator was worried about something that is not necessarily important for you to worry about. Right. So this is the intuition you want to get. Sometimes if your goal is just to predict the label instead of understanding the data, you may worry about the density function. Okay. Density function is for you to understand the data. It gives you a picture about where the mass of the data is, right? And how they spread out in their space, and where do you see the most representative pattern of the data, and so on and so forth. And all this may or may not be useful for making prediction. Okay. All right. So that's basically what happened here. Okay. It is doing its best job in estimating a conditional probability, but the boundary may or may not be the best. In fact, it is not the best, because if I now use the same design of the features, same feature, the information I got from data is the same, but I use a different optimization function, which is to optimize directly this structured decision boundary, not a single decision boundary. Okay, it's a structured one. You can imagine them in the high-dimensional space. Then I can push down the label to here. Okay. So same model trained in a different way generates you this much difference. Then the nice thing about M-cube network is not stopping here, right? Because remember, M-cube is a version of the support vector machine, and we have many other properties. I will answer your question in a second. There are many other properties of SVM. For example, people will argue, well, in SVM, I can introduce a nonlinear separation boundary for free by using a kernel trick, right? So actually, once you use a quadratic kernel or some other kernel, you actually indeed push the error down pretty well, right? And it actually already dominates the CRF, almost as good as this one, maybe, yeah. But Ben Tasker's answer is that, well, you do it here, I can do it here as well. This is also based on a quadratic optimization problem who still exposes you the inner product between feature vectors. You can apply a kernel on that, right? So it gets you here. Right. So this result actually was very exciting, a decade ago when people actually see that this is a graphical model that is behaving like a support vector machine and also allow you to apply kernel tricks and reproducing kernel Hilbert space theory and all stuff like that, right? And that actually generates a lot of excitement in studying that. And so you can see the reduction is quite dramatic. It's not about 1 or 2% of the error that you usually see in the incremental paper. This is a pretty big breakthrough. And the same kind of experiment behavior was also observed in some other texts. In hypertext classification, again, you have this highly structured prediction where I didn't study this problem carefully, but my understanding is that if you make predictions on each of the entity in here, their label are dependent on how you predict the other people. Okay, say these are web pages, and this is my homepage, this is my student's homepage, and then when you are predicting who I am and who they are, you may want to actually predict in the context, right? If I am a basketball star, then these people are less likely to be PhD students, right? But if I'm a professor here, then they are mostly PhD students and so on. And again, you can see the score from SVM to this is I think it is a likelihood-driven Markov random field, a Markov network, and this is the M-cube network, which is a Markov network trained with margin loss. You can see the huge drop of the error. All right, so that's the first part of lecture. I should now take your question over there.
I was just going to ask, if you go back a few slides. So you said a number of times that one more. You said that the models were the same here, they had the same features, but I just want to be clear that the SVM on the left versus the two, like the CRF and the M-cube on the right, the difference is that
the SVM and this, of course, are not using the same feature because here you don't have structure.
And the additional features on the right are like between
the pairwise features, yeah. But these two actually have the same feature, right? So yeah, the argument against CRF is due to a different loss, and the argument against the SVM is due to more features, and the more feature come from graphical model. Right? All right. So this is very exciting, and now let's see what more we can do about that. I think this in my opinion, the importance of this line of work is really to open up the possibility of training graphic model alternatively, going beyond likelihood, right? And now let's do a quick review, right? So you have now at least a likelihood-based estimation and a maximum margin-based learning both on graphical models. And then you have these competing advantages and the disadvantages, right? I just don't want to read it out. You can go back and review. But now people become more and more greedy, right? So, after all, still likelihood method had advantages. If not for a predictive purpose, yeah, I do want to understand the data while doing good prediction. What should I do, right? I cannot get the good side of both ends. And so maybe that's iffy. People say you are too greedy. You should choose one or the other. Either you do prediction or you understand data. So there is still a choice. But there are some problems which you don't even have a choice. Say I have a problem which has internal hidden structures. Okay, and I may have a partial label. The label wasn't completely available. Then SVM is not designed for that. SVM is a purely supervised learning problem with no definition of hidden variable, because it is not probabilistic. What do you mean by hidden variable? Something not observed, then you shouldn't bring that into the model, right? There isn't a distribution on that. But on the likelihood-based approach, graphic model, in fact, a good role, a function of graphic model is to help you introduce systematically hidden variables, like in SVM or in HMM, for example. You have this hidden variable of chains, and then you suddenly make the problem a lot easier. So this is a huge advantage of graphic model for hidden variable is not recovered in here. Right. But on the other hand, the SVM has also important advantages, especially the kernel trick. Not before long, of course, now we know how to graphic model with kernel. Remember the few lectures before, we talked about non-parametric graphic models. But that was invented 2 or 3 years ago. But 10 years ago, people don't even know graphic model go with kernel at all, right? And so what if I want to do non-parametric modeling and all that? Right, so there is this kind of need for seeking an approach that integrate maybe hopefully. Can we, for example, learn a model that is both maximum margin and maximum likelihood? That's kind of the problem. So it was a few years back, when a postdoc was working with me, we actually got pretty fascinated by this problem. And then we look into literature to see whether there are early solutions to that. So we find this paper by Yakala. It's a very obscure paper, somehow lost in the literature, not appreciated by too many people, as it should be. They invented a framework called minimum entropy discrimination. Okay, and what they do is to turn the SVM into a probabilistic estimation problem rather than a point estimation problem, and then they introduce something that gives you the hope of modeling the likelihood of data. Right. So what they do is the following: instead of learning a single estimation of W star, which is the weight of the SVM, I'm going to learn a distribution of PW. That's the first extension, distribution of the weights. And therefore, my prediction is going to be a model averaging problem. I'm going to now, still use this, predictive loss function, this f, but I'm going to weight it over the probability of the weight. So that's pretty natural. If you have a distribution, that's probably the direct advantage you can have to model averaging. But the way to learn this P of W rather than the point estimate of W is very interesting. They're going to do this. Okay. In fact, this I should actually put just W here to make things simple, because there are some additional auxiliary random variables. Just imagine it's W. Then the goal to the approach to learn that is to use this entropy minimization argument. I want to set a prior of the W, and then I'm going to learn a posterior distribution of the W, which minimizes the KL divergence between the posterior and the prior. What does that mean? I think in our early lecture, we basically say the minimum entropy argument is allowing you to inject minimum assumptions, okay, or maximize the randomness of the outcome, right? And then, of course, simply by minimizing the KL is not enough. I'm going to make sure that the resultant, distribution of predictive function should also satisfy the margin constraint in here, right? So this is called the expected margin constraint. Okay, the margin was originally computed for a singleton W. Now they are expected over, averaged over the P of W, right? So you can see this is a good replacement of the SVM. SVM basically are doing mean of W, and here you have YIF minus this to be 0. This is the original margin constraint. And now I'm replacing this with the minimum entropy loss and replacing this margin constraint with the expected margin constraint. Okay, and the whole reason is because I'm replacing now the W star into a P of W. So that's basically a framework they produced. They show some results of the estimated PW to be a better SVM with a more stable kind of behavior and so on and so forth. But the calculation was a little bit complicated, and the performance gain wasn't like what you see before. in the SVM versus structured SVM, say 10% improvement. So this work wasn't really appreciated overwhelmingly. But it's a nice paper in the literature. So now we ask, can we basically extend this framework, which is a probabilistic version of SVM, to the maximum margin Markov network, the way Ben-Tasker did from SVM to the structured SVM? We just asked a simple question. Okay, and the answer is very, very simple. You just need to follow the same kind of design principle they used. You are going to now also estimate a W, but this W now is built on the structured features from data, right? So you have this. We're going to now, instead of learning, P of fx, I'm going to now learn P of W of fxy, which is a feature vector, if you remember, right? And but other than the feature being different, W still have the same kind of behavior. So I'm going to still minimize the KL divergence in here, and then I'm still going to actually ask the PW to satisfy a margin constraint. Okay, in here it is basically in the space of distributions rather than in the space of all possible values of W, right? So these are the distribution which must respect the expected margin constraint. And here I have also a slightly more fancy term to control the margin effect. I'm going to have a function over the margin so that they can also be minimized. And then once I have the whole thing, I'm going to use it, okay, in this typical structured SVM way, but with an expectation over distribution. Okay, so this is a model which we call the maximum entropy discrimination Markov network. Right? It is a Markov network, as you see in M-cube network. It is discriminative, just as you see in the Ben-Tasker's model, but it is also maximum entropy, as you can see from here. So that's a very simple conceptual extension. And then this is just a conceptual picture about what are you trying to solve. Now you are trying to solve basically a optimum posterior distribution of the W, and it is satisfying the expected margin constraint. Each of these constraints defines a feasible space, and it is the intersection of all that. You are going to find a projection from here to here, and this one is the prior in here, and this projection is the KL divergence minimizer. Okay. All right. So that's basically the problem, and now the solution is dependent on what kind of model or kind of assumption you make. For example, this P of 0, okay, is something you can use as a tuning knot. What is the prior distribution of the W? Okay. So let's look at the example. First of all, there is a generic solution in a symbolic sense to this problem. After all, this is a constraint functional optimization problem, right? And I can use Lagrangian theory and to really give a closed form solution in the symbolic sense. So here is the solution. I'm not going to show you how to derive it. You know already do that, right? So you build a big Lagrangian by putting together the loss and the constraint, and then you take a derivative. In this case, the derivative is not over parameter, it's over a function. Therefore, you do variational derivative, right? And then you try to look at the fixed point, and then you put together the solution. And the solution looks like this. It's actually quite interesting. This is the posterior of W. It's actually taking the following form. You see here the prior, okay, multiplied with this term, okay. And if people are still familiar with the Bayesian inference, the posterior of a weight in the Bayesian sense equals to the prior times what? Times the likelihood, right, of the data given the parameter, right? That's basically a Bayesian estimation. In here, you can see they are roughly, correspondent. You still have the prior, but it is multiplying with something which is, of course, not a likelihood of the data, because here we are having all these margin constraints and all that. If you look at that, look at the details, it is taking this form. Very, very interesting. So you have a bunch of weights alpha, and this is what? This is just the margins basically, okay, over every training point. Okay, so I'm summing over all the i's, summing over all the configuration of y. Okay, so these are the actual realized margin on every possible label, and you are doing this. And what's the value of alpha? Well, alpha actually is the solution to this dual operation problem, which I put it in a very symbolic form. It can be very complicated. And from here, what do you get? Well, what you get is that first of all, this distribution, posterior distribution, is in the exponential family distribution, right? And secondly, it is a weighted sum of support vectors in here, right? Because later you will actually see something very interesting. This alpha, actually solving that corresponds to solving a support vector machine problem where only a few alphas can be non-zero, okay? And if you remember the KKT condition in SVM, what is the nature of, I bet you probably see this equation before, right, in the KKT condition in SVM. It is called the complementary slackness condition, where if this guy is not zero, then that guy should be zero. And if this guy is zero, that guy cannot be zero, right? Means what? Means that if this particular y is not a support vector, then its weight is zero. And if it is a support vector, then it has a non-zero weight, right? So you can see this same thing appeared in here, although in this very strange place that defines a exponential family distribution. So now I'm going to plug in one instance. Let's assume that the feature function takes this form as we have in the structured SVM. And let's take the prior to be a standard Gaussian prior. And then the solution is very interesting. So here is the solution to the posterior of W. It is actually taking the form of a Gaussian. Okay, the prior is a Gaussian. The posterior is also a Gaussian, but with a shifted mean. That is defined by this. It is defined by the weighted sum of some support vectors. And what does alpha correspond to? Well, alpha corresponds to solving this problem, okay, which is exactly the SVM problem, the support vector machine problem, right? If you go back to revisit that M-cube network, this one is the same as P4. Okay, so it means that you are now getting a posterior distribution of the weights, and the coefficients in here is equivalent to solving the SVM problem, the structural SVM problem, but what you get is a posterior distribution of the weights rather than a single estimation. And then, of course, when you are making the, it looks fancy that you have this posterior distribution of W rather than a W star. But when you go to use it, you are going to basically do this, right? You are going to make an average prediction. And the average prediction is equivalent to making a prediction using the mean estimation of the weights. Therefore, you are actually using this particular weight as the decision boundary weights, which gives you the same as M-cube network. So what does this mean? This means that effectively, when you are making this assumption, okay, here you have the same design of the feature as a M-cube network, and you have the same box constraint over the slack variable in SVM, and you have a trivial prior, which is standard Gaussian. Then your learned model is just the M-cube network itself. So what does this mean? It means I didn't gain anything. Right? I basically invented a very, very elaborate framework for probabilistic plus margin-based learning, and I got something the same as a maximum margin Markov network. But this is actually a very nice result because it means that there is a reduction path that my very fancy framework can reduce to what is people know about that has a good property. What if I don't reduce? I go with some fancier version. For example, I introduce a different prior. Right? So that's basically what gives you the advantage of this more flexible framework, where we can replace, for example, the prior with a different one. I think I have a slides here. For example, I can now replace the prior with a Laplace prior. Laplace prior is this prior which encourage a spiky distribution, right, rather than a more spread heavy tail distribution over the over the coefficients. And it turns out that once you use this, you get a max margin Markov network with a L1 shrinkage kind of property, meaning that the average W is now a sparse vector. Many features become having zero weights. Okay, and of course here I have the other advantage because you have a Bayesian model, you have a posterior distribution. Therefore, you can prove a nice generation bound using the pack-based theory. And also the third advantage that you are now learning a P of W, right? It is a probabilistic model. You can also generalize it to have a graphical model with hidden variables. Okay, and at the end of the day, what you do is to integrate all those hidden variables and also the W and make a prediction. So we're going to talk about that in next lecture. So what you learn now is not a SVM, it is a distribution of SVM parameters and also possibly a distribution over other hidden random variables you care about. Okay, that's why you see a nice connection of more general graphical model learning. So let me talk a little bit more about this Laplace maximum entropy distribution Markov network, because that's the first piece that we use to argue for an advantage of this framework over either the CRF or the maximum margin Markov network. So in this case, we introduce a prior, okay, that is taking this form. And you can see this form actually has a greater mass at the small value, okay, and the smaller mass over bigger value. That basically means a shrinkage effect. I encourage the value to go to zero, right? And as a result, now your posterior mean of the weights is taking this form, okay, 2 lambda over lambda minus lambda eta square, and the eta is basically this weighted sum of support vectors, right? Okay, so why it is becoming sparse? Well, you can actually plot this value against the magnitude of the eta over its posterior probability, and you can see that when the lambda is taking a small value, then the posterior mean actually gets a greater penalty. It will be divided by a bigger value, therefore it will push down to a smaller value. But if this lambda is a big value, for example, then it is actually going to remain big, right? So what does it mean? It means that greater weights will remain greater, and the smaller weights will be even smaller, will be pushed down to zero, meaning that if you have a small weight, they are more likely to be noise, and I'm going to ignore that. This is very much the same what a lasso regression would induce, in penalized small weights and get them to zero. And just compare in the Gaussian maximum entropy network, which is equivalent to the M-cube network, you don't have this effect. The posterior mean of the weights is just the eta itself, which is the unshrinked version of the weighted support vectors. Right. So that's an advantage. We want to see whether it plays a good role or not. And here are some more insights about why that shrinkage is happening. Here, well, you can do some algebra and show that what you actually solve as a maximum entropy Markov network with a Laplace prior is equivalent to solving a maximum margin estimation with this loss function. Maybe I will show here. So what you have here is SVM, right? And then you have this margin constraint. And here you have the L1 norm. This is called L1 norm SVM. And the L2 norm SVM is basically having a two norm. And for these two norms, you have this feasibility space, which one is generating a circle, the other generates a diamond, right? And this norm, which we call the KL norm due to our formulation, is actually taking this form. Depending on the number, the magnitude of the lambda, you can see the feasibility space are going smoothly from a rounded, spherical area region to a more cornered diamond region. Therefore, it gives you a smooth transition from rich penalty to lasso penalty. Okay, and that's why you actually get a pretty nice shrinkage property even using the following framework. Okay, so I think that's pretty much what we can conclude from this new model. It has basically what we call a primal sparsity due to the Laplace shrinkage effect, but also it is by itself a maximum margin Markov network because of the solution of these weights over the support vectors. Therefore, it is also dual sparse. Therefore, you at the end of the day get a solution which is both primal and dual sparse. Meaning what? Meaning that once you use the maximum discrimination Markov network to get a solution to the W, which is the mean basically of W over PW, then this guy has an interesting property, which is that it is both dual sparse, meaning that it is decided by a few support vectors, but also this W vector itself, okay, which are of weights, is also sparse, meaning that many of the weights dimensions are equal to 0. Okay, meaning that you actually can have a feature selection effect, over the model design. When you do the model, you design a lot of features to come up with the predictor, and now they have your feature selection properties. Right. So that's actually a nice framework. There are some technicalities in solving this problem, which I'm going to pass. I want to wrap up by giving you some nice results so that you can be hopefully inspired by the edited power of this new model. So we have this problem, and the experiment was done actually in a very, very elaborated way. Because there are so many prior work to us in doing structural prediction, it is very hard to publish a paper in this domain, right? Because you have all the competitors. You can solve the previous problem by CRF, which is already exists, by M-cube network, which also exists. Then, because we are arguing for the shrinkage version of the network, we say you can generate a penalty effect. Then the reviewer will ask, well, you can do the same penalty over a support vector machine or over CRF and over M-cube network as well. Why don't you do the same shrinkage over there and see whether they are good? So we were forced to implement all this. We have a CRF, we have the L2 penalized CRF, the L1 penalized CRF, the L1 penalized M-cube network. There isn't a L2 penalized M-cube network. Why isn't that? Because the M-cube network itself is L2 penalized. It is SVM. SVM loss function is this L2 normal W. And we were pushed to the point that some of this implementation itself is not even published yet. People don't know how to do that. So we actually published a few papers to just come up with the experiments. Like this one is actually a new paper by itself, the L1 structured SVM. Okay. But luckily, after we implement our version, you can see that in many of these contexts, the performance become even better, okay, than any of these predecessors. Okay. And also, it has this nice feature selection property that it picks. These are basically the way we generate the data, and you can see that we pick the right feature and having all other features properly with 0 weights. And the other models, have either no ability to do feature selection because they also have non-zero weights, or having a feature selection in here like the L1 norm M-cube network, but their predicted performance is worse. And there are some other properties such as sensitivity to regularization and so on and so forth we can discuss in next lecture. So to wrap up, I just want to now show you this nice roadmap of generalizing graphical models, right? So we have this SVM, and going this direction, we can use the graphical model technique to come up with a structured version of SVM. And we can use a probabilistic argument to make a Bayesian version of the SVM. And now we are here. We are basically bringing in both the structure and the Bayesian ingredients to make now a structured, maximum margin graphical model. And there are some open problems I will discuss later. But in our next lecture, I'm going to show you that this framework is not about only training what I showed you earlier. This new framework of estimating graphic models, when you are able to implement it for any model of predictive task, it guarantees you almost to always outperform a simple SVM-based implementation or a likelihood-based implementation in all the cases we tested so far. So I'm going to tell you how to do that next lecture. Okay, so that's all for today.
I have a question on the L2 norm CRF.